In high-throughput cloud architectures, Amazon S3 functions as more than a location to store files. It acts as a real-time event processing engine. Systems that treat S3 as a passive repository frequently encounter latency bottlenecks. To maintain high availability, storage operations must be architected to drive downstream logic and handle massive concurrency. High-performance S3 design requires precise mapping of asynchronous delivery pathways and a strict adherence to baseline partition lists. Over the next 10 minutes, we will deconstruct the physics of S3's physical partitioning and implement advanced optimization techniques, specifically multi-part uploads, edge routing, and byte range fetches. Mastering these mechanisms allows you to engineer S3 as a reliable backbone for high concurrency systems, rather than a single-threaded bottleneck. S3 publishes asynchronous notifications when specific bucket events occur, such as object creation, deletion, or restoration. This diagram shows the exact JSON payload generated during an event trigger, containing bucket metadata, object key, file size, and the e-tag. Suffix filtering isolates specific workflows, configuring applications to publish events exclusively when new objects ending in a .jpeg suffix are uploaded. S3 routes these events directly to three primary integration targets: AWS Lambda functions, Amazon SQS queues, or Amazon SNS topics. These are asynchronous pathways. While delivery typically occurs in seconds, it can take a minute or longer under heavy load, making them unsuitable for ultra-low latency synchronous transaction paths. This architecture map details the security requirements for event delivery. You must configure explicit resource-based policies, granting the S3 service principal direct permission to execute specific target APIs, like Lambda.InvokeFunction or SQS.SendMessage. Without these explicit permissions, S3 lacks the authority to push the JSON payload. Events fail silently, halting the execution of all downstream logic. Because event notifications are asynchronous, your application logic must account for delayed, retried, or out-of-order event deliveries. This requires designing downstream consumers for item potency. If an SQS queue receives a retry of a creation event, the application must identify the duplicate rather than creating a second database record. This timeline shows how S3 manages event ordering. Embedded in every payload is a unique sequencer hexadecimal string defining the absolute chronological order. Programmatically, your consumer must compare these strings, retaining the higher hexadecimal value, the most recent state, and discarding the lower. Comparing these sequencer strings is the only reliable method to discard stale events and maintain state consistency across your event-driven networks. To increase throughput, we must map requests against S3's horizontal partitioning architecture and its baseline performance limits. S3 manages request rates at the prefix level. A prefix is defined as any path segment situated between slashes in an object key. This distribution map displays baseline performance per prefix, 3,500 write or delete operations and 5,500 read operations every second. While individual prefixes have these caps, S3 imposes no limit on the total number of prefixes you can create within a bucket. This 4-prefix tree demonstrates the math. Distributing read traffic across 4 prefixes achieves an aggregate 22,000 GET requests per second. S3 dynamically monitors load. When thresholds are exceeded, it automatically splits partitions, allocating dedicated backend storage nodes for parallel traffic. The established best practice for maximizing this architecture is injecting randomized unique hashes at the beginning of your object paths. This distributes incoming traffic across thousands of distinct prefixes simultaneously. By spreading the load across the entire storage cluster, you bypass the performance ceilings of individual prefixes and achieve aggregate throughput that matches the demands of your specific dataset. Operating at cloud scale also requires mitigating network instability when transferring massive multi-gigabyte files across the unpredictable pathways of the global public internet. Multi-part uploads split a massive file into smaller independent parts for concurrent upload. If a network drops, you only re-upload the single failed chunk. Boundaries apply: recommended over 100 megabytes, mandatory exceeding 5 gigabytes, and capped at 50 terabytes. If a multi-part upload fails to complete, S3 retains the orphan chunks in storage, generating ongoing billing charges. Deploying S3 lifecycle expiration rules to automatically clear these incomplete parts is a standard cost control measure. Transfer acceleration routes data to local AWS edge locations, then via AWS's private fiber backbone. With parallel multi-threading, transfer speeds jump 500%. Direct ingress is free. Transfer acceleration adds 4 to 8 cents per gigabyte, while CloudFront outbound routing drops S3 query charges 7 times. Combining multi-part parallelization with private backbone edge routing yields consistent speed and resilience, even when transferring massive datasets across global networks. On the retrieval side, pulling massive objects using a single, sequential download stream is inefficient and consumes significant thread time. A byte range fetch optimizes retrieval. By injecting specific byte ranges into HTTP GET headers, your application requests strictly isolated segments of a file across multiple concurrent threads. If a connection fails, your application only retries fetching the exact interrupted byte range. Byte range GET requests can target massive archives. Because these formats store index maps at the end, we request just the final kilobytes to extract metadata. Using this index, your application executes targeted block requests to retrieve only the specific data required by the user. Executing byte range fetches reduces network egress costs and improves response times by decoupling file discovery from full payload transfers. This matrix summarizes the mechanics of an active storage engine. We use structured JSON event notifications to drive asynchronous workflows and maintain item potency by comparing hexadecimal sequencer strings. We achieve horizontal scale through prefix hashing and mitigate latency using multi-part ingestion and byte range fetching. S3 scale is not automatic. The throughput and reliability of your data layer are a result of deliberate systems-level engineering choices. Once you master the mechanics of high-performance storage, the final hurdle is managing these architectures across billions of objects at enterprise scale. In our third and final video, we will analyze methodologies for fleet-wide governance, breaking down S3 batch operations, exploring S3 inventory, and S3 storage lens.